So this is second term physics. We're looking at some optics. So we have two laws of reflection. The first law of reflection is that the incident ray I, the reflected ray common R, and the normal capital N are all in the same plane. The second law of reflection is that the incident angle theta I and the reflected angle theta common R are all equal. So if you look at the diagram, you're going to see the surface that the ray is reflecting off, and you'll see that the angle the two rays are at against the normal are equal to each other, right? So the normal is 90 degrees to the surface. So anytime you hear the word normal, it means 90 degrees, right? So the two laws of refraction, the first law of refraction is that the same law from reflection, you repeat it, except you change the word reflected ray to refracted ray, right? Everybody understand that? So the refracted ray, and I use capital R for the refracted ray, right? So just now, so we have here now the ratio of sine of the incident angle to the sine of the refracted angle, theta capital R, is a constant n. Therefore, common n, which is the constant, is equal to sine of theta I divided by sine of theta R. So you need a calculator for this question. You need to buy a scientific calculator. You cannot use your cell phone. Let's look at the definitions. Reflection is the change in direction of a wave. Refraction is the change in velocity, which is speed and direction of a wave. So we could see here a light is moving from air to glass, right? I have a demonstration for this, but I didn't bring it. So we would have the ray now meeting the point on the surface, and that point on the surface has a normal on it, an imaginary normal. That imaginary normal again is 90 degrees, right? So there's an angle theta I and there's an angle theta capital R, right? So you have N1 for the air and N2 for the glass. That's the constant from the second law, right? We call that Snell's constant. Okay? So the second law of refraction is actually called Snell's law. Okay? So from optically less dense medium to more dense medium, the theta R is less than theta I. From more dense to less dense, theta R is more than theta I. So if you look at the diagram here is different. So with this diagram now, the incident ray is inside the glass. Okay? And the refracted ray is outside the glass. So we switch the origin of the ray. So if I was to do out an equation and I use N1 and N2 for air and glass, I will end up with sine theta I divided by sine theta R equal to N2 over N1. And this will mean that if N1 is air, N1 is equal to 1. So N2 divided by 1 is equal to N, which will give me sine theta I divided by sine theta R. And then I have, if N1 is water, N2 is 1. So I will get 1 over N1, which will give me 1 over N equal to the same sine theta I over sine theta R. So this second equation is for the second example where the incident ray is starting inside the other object. It could be water, it could be glass, right? So then now I have where I could substitute sine theta I for lambda 1, which is the wavelength, and I could substitute sine theta R for lambda 2. right? And I could also substitute them with velocity, because remember we said, well, I said refraction is change in speed and direction, right? So the speed is represented by the speed of light, c, and v is the speed of light in a medium. So c is the speed of light in air or a vacuum, and v is the speed of light in another medium, right? So a medium could be glass or water, okay? But if it's not glass or water and it's air or space, the speed of light is what we call c, okay? So that c has a specific constant value of 3.0 multiplied by 10 to the power 8, which is 30 million. That's 30 million, right? No, that's 300 million. 300 million, right? So that's a constant value. So the V, that V could vary, but the C is always constant, right? Good, nice. If I have a material that is in air, and N1 of air is 1, right? And I want to find the refractive index of the material, and I have the angles of incidence and refraction at 40 and 10, I can use Snell's equation. N is equal to be sine 40 divided by sine 10, and I'll get 3.70 as the refractive index of the material. So the symbol for refractive index is N, okay? Then, if I have, let's say I have refractive index is equal to be 2.80. I have theta I is 30 degrees. I want to find theta R. So I use Snell's equation again. I rearrange the equation. So I carry the sine theta R from the right hand side to the left hand side. So I have N sine theta R is equal to be sine theta I. And then I make sine theta R the subject of the formula. So that is now equal to be sine theta I divided by N. And then I put sine 30 over 2.8. So I substitute the given values. Sine of 30 is always a half. That's a constant value. So 0.5 divided by 2.80 will give me 0.179. And when I sine inverse both sides of the equation, I will get theta R is equal to be 10.3 degrees. Okay? And then, if I come here, I have a wave started inside of the material and leaving the material. Okay? So the material refractive index is 1.60 and the incident angle is 20 degrees. The refracted angle is unknown. So I want to find the refractive angle again. In this case, I start off with this equation, which is different because we started from inside the material. And I can rearrange the equation and I carry the sine theta R across. It will be divided by N. And then I make sine theta R the subject of the formula and I carry the N to the right hand side. Okay? So when I substitute the values, I'll have 1 over 1.60 equal to the sine 20 divided by sine theta R. So 1.60 multiplied by sine theta R is equal to the sine 20. When I carry the 1.60 across, as seen here in red, I will end up with 1.60 multiplied by sine 20. Sine 20 is 0.342. When I multiply them, I will get 0.547. When I sine inverse both sides of the equation, I will get theta R is equal to be 3.2 degrees. So you must always put the degree sign as a unit, right? Otherwise you'll lose marks. So, now remember, the refractive index is a ratio, so it doesn't have any units. It's a unitless quantity. A wave refracted from a wavelength of 6 nanometers to 4 nanometers, find the refractive index and the new velocity. So when I use the same equation that I showed before, n is equal to be lambda 1 over lambda 2, and I put the two wavelengths, I'll get 1.50. So now I'm using the other equation, or I'm using n equals c over v. So when I rearrange, I get nv is equal to c, I get v is equal to c over n, and I substitute the speed of light divided by the refractive index, and I get 2.0 by 10 to the 8 meters per second. Right? So everybody see how that goes?
Yes, sir.
Nice. Total internal reflection is when an outgoing wave incident angle exceeds the critical angle C. Parallel transmission occurs if the incident angle is equal to the critical angle. In that case, the refracted angle is equal to 90 degrees.